Hey, wherever you might be, welcome back to another exciting lesson of calculus. So far, we have gone through a lot of different rules of derivatives. Okay, we've talked about the sum and difference rule, the constant multiple rule, the power rule. We've talked about the product rule, the quotient rule. Okay, we've also talked about a lot of the trig functions, the derivatives of the 6 basic trig functions: sine, cosine, tangent, secant, cosecant, cotangent. Okay, that was actually last lesson. Today, I'm going to introduce one more rule to you. It's called the chain rule. And the idea of the chain rule is to help us take derivatives of composite functions. So you know the kind when you have a function inside of a function. We talked about that at more towards the beginning of the year of how to deal with continuity of composition of functions. But now we're going to get into taking the derivative of composition of functions. And the chain rule helps us do that. Now I'm going to tell you right off the bat that the chain rule is going to be a 2-part lesson, because at first it takes a little bit to grasp it. So I'm going to show you kind of the logic behind it, and then in the next lesson I'll show you a quicker way to approach it. But that quicker way isn't going to mean anything to you without understanding the logic behind it. And believe me, understanding the ins and outs of why it works is so much better than understanding that it works and how to use it, okay? Because it's going to give you a better understanding of other things later on, especially when we talk about inverse functions, okay? So with that said, let's go ahead and get started. First thing I want you to do is I kind of want you to take the derivative of both of these functions and see what you come up with. So go ahead and pause the video and work these out, and when you're done, come back and push play and see how you compare to me. All right, hopefully you've done these. In the first case, we got the derivative of 3x plus 1 squared. Now you can recognize that this is actually a composition of functions, and I'm going to show you how to use a chain rule to get this derivative. But before we do that, we're going to have to figure out how to take this derivative without the chain rule, using the rules that we do know, okay? So what I do know is that this is equivalent, if I expand this out, to 3x plus 1 times 3x plus 1, right? And from here, I could actually use the product rule if I wanted to. So the derivative of the first thing would be 3 times the second thing, which would be 3x plus 1, plus the derivative of the second thing, which is 3, times the first thing, 3x plus 1. And then we can simplify that pretty easily. That's 9x plus 3 plus 9x plus 3, which turns into 18x plus 6. So we have our derivative there. You could have also, if you wanted to, expanded all that out, multiply that out so it's a trinomial. So you get 9x squared plus 6x plus 1. And then taking the derivative of that, all you would have to do is the power rule. So you end up with 18x plus 6, the same thing. Okay? So hopefully you got that as a simplified answer. I'm going to show you the chain rule in just a minute. But I would argue for this particular case, because it's polynomial, the quickest way to do it would actually be this method, the expanding, simplifying, and power rule. But I want you to see the pattern here so that you can apply the chain rule to other places that aren't so simple. Okay? Let's go ahead and take a look at the next example. It's very similar to that previous one. We have cosine of squared x. Now we're going to have to expand this to say cosine of x times cosine of x. And then we'll use the product rule again. So the derivative of cosine is negative sine, and then times the second thing, so times cosine, plus the derivative of, put parentheses around these, that's a good idea. Derivative of cosine is negative sine times the first thing, so times cosine. And then you can see we can simplify this. These are the same term, negative sine cosine, so we can combine those and say that's negative 2 sine of x cosine of x. And so that's our derivative there. Okay? Now there's something very unique about this particular one that you might be able to see. Looking at the derivative, looking at the function and looking at its derivative, seeing something going on there and thinking about the idea of the composition of functions. All right, with that said, Let me double check to make sure everything is good before we go on. We got 18x plus 6 here, and I did it the other way there. Expanding this using the product rule. Same exact thing. Notice though, in the notes, I just rearranged the cosine and the sine, and that's actually going to lead us into seeing something a little bit more with what's going on here, okay? So let's go ahead. Oh, here we go. Well, let's try this one. I want you guys to pause the video. I don't want you to use a calculator right now. I want you to just try and think of the derivative of this on your own and see if you can come up with it. And then when you think you have an answer, come back and compare it to mine. My guess is you're going to be wrong, and that's not an offense to you. That's just something that's important to learn right now, okay? I'm having you do this so that you can use it as an opportunity to learn. All right, we are looking for the derivative of 5.2 tangent of 2.4x and then plus 3.7. So we're looking for the derivative of all of that. My guess is, this is how you approached it. This is my guess, okay? You said, well, 5.2 is a constant, so I'm just going to carry that out. I know the derivative of tangent. The derivative of tangent is secant squared of, we'll say 2.4x, because that's what we're taking the tangent of. And then the derivative of 3.7 is 0, so I don't have to write that down. My guess is that's what you wrote, okay? If you were honest and you did this yourself. But if you were to use your calculator, and like I've said before, you shouldn't be using your calculator to find a derivative function, but it might be a good idea to explore here. If I do that, I actually end up with, come on now, there we go. My guess is, again, I can predict the future here, I'm pretty good at this, that you got that, right? The calculator's answer, if you're using a TI-89 and it can produce a derivative function, says 12.48 secant squared of 2.4x. And so you can see that your answer and the calculator's answer are not the same, but is there something that you do see the same? Well, you do see that secant squared, and then the argument for secant squared, the 2.4x, is still there. So we have the secant squared 2.4x in both. What happened with the 5.2 and the 12.48? 5.2 times 2.4 is, what is that? That's 12.48. Look at that. Interesting. So we know that the calculator is right, not because we just believe calculators, but because I'm guiding you through this. That's the correct derivative. So we know that yours is wrong. And so the question now arises, why did we multiply the 2.4 by the 5.2? Why did we do that? Well, that is part of the chain rule. Don't try and think too far ahead here, because I don't want you to miss something that's very important, okay? But let's go ahead and go on and define the chain rule before we get too far ahead of ourselves, okay? Like I said, the chain rule is used to find the derivative of a composition function, okay, or composition of functions, okay? So if I said let f of x equal g of h of x, so that's the composition, then f prime of x equals g prime of h of x times h prime of x. What? I'll clearly define that a little bit more in a second. But I want to write it this way because I think that this is so important to see. If I say that y is my function, and it is a function of, let's say, u, or sorry, let me clearly define these things. That y is a function of f, right, in terms of u, y is in terms of u, and u is a function in respect to x. Okay, so u is a function. It's not just a variable. It's not just a number. It's a function in and of itself. So we have a composition of functions. So technically we would write it like this: f of u of x. Okay? What we want to do is write this in Leibniz form. We want the derivative of y. We want the derivative of y in respect to x. And this is why Leibniz form is so nice to understand why these things work. This is our goal, dy dx. Well, what it's saying to do is to take the derivative of f, in respect to u. So it's kind of like saying treat u as a variable, like u is the variable of f, okay? So these don't work. This doesn't work, right? This is not the same thing. So we're going to multiply that by du dx. And so we can see here, now we're taking the derivative of the function u in respect to x. So in this case, we're treating u as the variable. In this case, we're treating u as the function and x as the variable. But watch what happens so beautifully. We see that the du's cancel each other out. The du cancels each other out. And so we're left with something that's logical, that the derivative of y in respect to x is the derivative of the function in respect to x. It might be better to just say this, okay? Maybe I'll rewrite it this way. Maybe look at it in a different light. Instead of saying y equals, let's say I want the derivative in respect to x of y of u of x. So you can see that y is the function, and we have an inside function here, okay, a composition. So we're taking the derivative in respect to x. So our final answer should be dy dx. Well, dy dx is equal to dy du times du dx. That's just a logical statement, right? I mean, the fraction reduced and you're left with dy dx. That's fine. But pay close attention to what that means for the function. It's telling us to treat the outer function as a function and take the derivative of that where the inside is a variable. Treat it as a variable. Then multiply it by the derivative of the inside function in respect to x. So in this case, treat the inside function as a variable. In this case, treat the inside function as a function in respect to the variable x. Okay? So that's kind of the meaning behind it, or the reason behind it. But let's go ahead and take a look at an example of this. We've got y equals 3x squared plus 1 and then squared. Okay? We're looking for dy dx. We're looking for dy dx. Now, obviously, you can expand all that and then just do the power rule or do the product rule, whichever method you prefer. But our goal is to look at it through the chain rule so we can verify it. Well, we know that dy dx is equal to dy du times du dx. What does that mean? That means treat this whole thing as a function where the inside, u, is the variable. So here's how we're going to look at this. We're going to say, let u equal 3x squared plus 1. Let u equal 3x squared plus 1. So what do we have here? If I were to rewrite this function, I would get something that says y equals u squared. Right? I just replace the 3x squared plus 1 with u. Now, isn't it easy to take that derivative? It sure is. Well, the chain rule says if I want dy dx, I've got to figure out what dy du is. Well, here's a function of y in respect to u. So that means treat u as a variable. So what's the derivative of u squared? The derivative of u squared is 2u. Okay? So I've got dy du. I also need du dx. Well, that means I need a function with u and then the variable's x. Well, that's what I have right here. So I could say du dx, well, x is my variable. So what's the derivative of this guy? The derivative of 3x squared is just 6x, and the derivative of 1 is 0. So here I have du dx, in other words, the derivative of the function u in respect to the variable x. I have the derivative of the function y in respect to the variable u. And when I put these two things together, dy du times du dx, I get dy dx. I get the derivative of y in respect to the variable x. And so I end up with the derivative of this guy pretty nicely. So I can just substitute now. Dy du is 2u times du dx is 6x. Now from here, we don't want any u's in here because we want the variable to be x. So we're going to take u and plug it back in. So this will say 2 times u, or 2 times 3x squared plus 1 times 6x. And then obviously we can simplify that further if we wanted to. I'm not going to go too far with this, but we'll just say that that is as simple as I want to get it. And again, you can go through and expand this all out, 9x to the 4th plus 6x squared plus 1, taking the derivative of that. That would be 36x to the 3rd plus 12x. And so when I distribute that, I get 36x to the 3rd plus 12x. And again, this way is way easier when we're talking about polynomials. But the idea is to see the chain rule in action and to be able to verify it with something we know. Because when we go on to other things, we won't be able to verify it. Okay? So just quick recap. If I want the derivative of a function y in respect to the variable x, and you recognize a composition, what do? You identify the inside function. In this case, inside function is 3x squared plus 1. You take the derivative of the inside function in respect to the variable x. You take the derivative of the outside function, which in this case is y, in respect to u, so we're taking the derivative of this guy, and then you just multiply these two together because the du's will cancel out and you're left with dy dx, which is the same as saying y prime. Dy dx is y prime. Okay? All right. We're going to go ahead and look at 3 more practice problems. So I fully expect that you don't understand this completely yet. So if you need to watch through the first example to get another example of this before you try it on your own, go ahead. But if you think you can do it, go ahead and do it. Okay? So for number 1, it says that f of x is equal to cosine of x squared plus 1. Okay? Now I can't take the derivative of this because this is a composition of functions. I can't just use the derivative of cosine and call it done. I have something inside there. So remember, the first step is to figure out what the inside function is. The inside function, u we call it, is x squared plus 1. So inside is x squared plus 1. Now, if I want f prime of x, that's the same as saying what's dy dx essentially. Okay? The way I get dy dx is I say what's dy du times du dx. And so we can see the du's cancel out again. So what do I have to do with u? I have to take the derivative of it in respect to x. So that's pretty easy here. So we would say du dx is equal to 2x. And then we have to identify our y value. Well, that would imply that y equals the cosine of u. So we're just labeling f to equal y. Okay? So we end up with cosine of u. X squared plus 1 is u. So we have to take the derivative of y in respect to u, where y is the function and u is its variable. What's the derivative of cosine? It's negative sine of u. Now, we just multiply those two things together. So we end up with dy du is negative sine of u times du dx, which is 2x. And we'll simplify that a little. Well, first we have to get rid of the u. We have to replace u with its original expression for x. So that's negative sine of x squared plus 1, and then times 2x. And then that can simplify a little bit to be negative 2x times sine of x squared plus 1. So there is the derivative of a composition function. Okay, so go ahead and pause the video now and see if you can come up with number 2 and number 3 on your own. For number 2, it's a little bit different of a look, but that's okay. This is still doable. We've got number 2 says g of x is equal to radical 3x squared minus 5x. So we have g of x here. Our goal is to figure out what g prime is. Well, we've got to figure out an inside function. So we're going to say u, what's the inside? This is pretty easy. The inside is 3x squared minus 5x. And the outside then would be g of u. So I'll just say g of u is equal to radical u. Okay? We need to figure out du dx, the derivative of the u function in respect to x. And we need to figure out the derivative of the g function in respect to u. So those are our two things we have to do. The derivative of this guy is going to be 6x minus 5. And the derivative of this guy, remember this can be rewritten as u to the 1/2. So we use our power rule, 1/2 u to the negative 1/2. And then we could simplify this to say 1 over 2 rad u. Okay? Then we multiply these guys together because that will cancel out the du's and we'd be left with dg dx. And dg dx is just another way of saying g prime of x. Okay? So we'll multiply those together. We end up with negative 1 over 2 rad u times 6x minus 5. And then we want to replace the u value with what it's equivalent to in terms of x. So that'll be negative 1 over 2 radical 3x squared minus 5x, and then times 6x minus 5. And then we could simplify that just a little bit by saying negative 6x minus 5 over 2 radical 3x squared minus 5x. And so there is my derivative. Okay? There's no reason, no need to rationalize the denominator there. Our focus is on the calculus right now. Okay? So let's go ahead and make sure we are good with that answer. 6x minus 5 over 2 times 3x squared. Uh-oh, what did I do wrong? I did something wrong. Where did I go wrong? Oh, right here. I don't know why I put this negative here. dg du should be positive. So that negative doesn't need to even be there. That's fine. And so that is exactly what I got on there. So we're good. All right. So let's take a look at number 3 now. And again, if you didn't do number 3 yet, but you think you have a better understanding of how this works, go ahead and pause the video and try it. So for number 3, we've got d dx of cosine of sine of x. Okay. So we want the derivative of this function in respect to x. So let's identify the inside. Let u equal sine of x. That would imply that the function would be cosine of u. Cosine of u. So we need the derivative of u in respect to x, and we needed the derivative of y in respect to u. The derivative of u in respect to x, the derivative of sine, is cosine of x, and the derivative of cosine of u is negative sine of u. Then we multiply those two together, so we end up with negative sine of u times cosine of x. And then we'll replace the u with what we have here. So that'd be negative sine of x times cosine of x. And that's our answer there. Now, one thing I want to make clear here, this is a composition in and of itself. It's not saying negative sine times sine of x. If there was a multiplication sign that doesn't make any sense. That's like saying, hey, what's the square root times 5? That doesn't make any sense. Sine is an operation. It's a function on something. So we are taking the sine of whatever we get for sine. So we can't really simplify that. We can't say it's sine squared because that would imply multiplication, and that's not what we're doing between these two. So that is our answer for that problem. Double checking my work, make sure it's good. We end up with our answer there. All right. So hopefully you're kind of getting into a routine here where the goal is to identify the inner function, make it a composition, identify the inner function, take the derivative of that inner function in respect to the variable, take the derivative of the outer function in respect to the inner function, and then multiply those two things together and then replace the u with its original equivalent. So let's go ahead and go over an application of this stuff. And these kind of application problems are going to continue on. And if we can understand how the derivative and the second derivative and all that relates to real life context, it's going to really help us understand the calculus itself. We've already talked particle motion, but let's talk about a specific one here. The amount of water in a bucket is related to time such that W of t is equal to 1/3 sine of t, what is that? 1/3 sine of t cubed plus 22. So W represents the amount of water in a bucket in cubic inches. So we're going to say inches cubed is the units on that. And t is measured in, let's see, W is inches cubed, and t is measured in time in seconds, okay? So this is how much water is in a bucket at a given time, okay, over the interval 0 to 6. I'll go ahead and write that down too, 0 to 6. All right, the question is, when is the bucket being filled and when is the bucket being emptied? So here we have a bucket. Let's kind of draw a picture of this for you. And we have some sort of level of water inside that bucket. Okay, so we have water in here. And we have maybe a faucet or something like this. If I can draw a faucet. Probably not very good, but that's okay. We have a faucet where water is filling up the bucket from that faucet, okay? Then we also might have a hole in the bucket down here where water is coming out of the bucket. Okay? So we have water going in and water going out. And the reason that could be the case is because W represents the amount of water in the bucket. And because this is a sine function, it's some sort of function that's going to reciprocate. It's going to keep bouncing back and forth somehow. And so we're obviously going to get different levels here. So the question is, when is the bucket being filled and when is it being emptied? Well, we want to translate that question into calculus terms, into what's given here. W represents the amount of water in the bucket. When is the bucket being filled? The bucket is being filled when the amount of water is increasing. So let me write that down. Being filled implies W is increasing. Okay? If the bucket's being filled, that makes sense that there's more water in the bucket, so the amount of water is increasing. And then being emptied, we would say that is when W of t is decreasing. Okay? So that's the question. When is W increasing? When is W decreasing? Okay, so I'm going to go ahead and get rid of this, and I want you to recall that relationship between a function and its derivative. How do I know when a function, W of t in this case, is increasing? A function is increasing when its derivative is positive. A function is decreasing when its derivative is negative. Okay? Now, analytically, when we go to solve these types of problems, we can't solve analytically where a function is increasing or decreasing. We can solve analytically where a function is positive or negative. So whatever function we're dealing with, whatever question is being asked, you need to make sure that you are translating the question into a context where you're looking for positive or negative values, not increasing or decreasing values, okay, or increasing or decreasing intervals. So let's go ahead and interpret that. We would say that we are being filled when W is increasing, therefore we are looking for something like this. W increases when W prime is positive. Okay, and then W decreases when W prime is negative. We'll get there. But the bottom line is we're going to need to figure out what W prime is. We're going to need to figure out the derivative. So W prime of t equals, well, notice we have a composition of functions. We have an inside function here. So I'm going to do this work off to the side, and then I'm going to erase it. But we're going to have to use the chain rule here. So we're going to say let u, the inside function, be sine of t. So the inside is u. That would imply that W is equal to 1/3 u cubed plus 22. Okay, so let me go ahead and get rid of this because we're running out of room here. So there we have the inside function, and then the outside function is now in respect to u. Remember that we take the derivative of u in respect to time. So that would be cosine of t. And then we take the derivative of w in respect to u. So that would be u squared, right? Just power rule there, that's 0. And then to figure out what dw dt is, we would multiply these two together because that would cancel out, that would cancel out the du's, and we're left with dw over dt. So we end up with, I'm going to put this one first because that's not how we normally write it, u squared times cosine of t, and then we'll replace the u value with what it's equal to in terms of t. So that would be sine of t squared times cosine of t. So that is our derivative function. On the next lesson, I'll talk about a quicker way of determining the derivative using the chain rule, but it's not going to be beneficial until you understand how this breaks down, okay? Leibniz form, the du dt, dw dt, helps us understand how the chain rule works or why it works, and it's because the du and the du cancel out, okay? So there's my derivative. Now what are we looking for? We're looking for remember when the function is increasing and decreasing, in other words, when the derivative is positive or negative. Well, the way we go about figuring out positive or negative is we first answer the question, when is the derivative equal to 0? So we're going to go ahead and set this equal to 0. And this is a non-calculator problem because we can do this without a calculator. This is doable using our trig. And then we should recognize that this is going to be the zero product property, that when I multiply two functions together and I get 0, that implies that either the first function is 0 or the second function is 0. Now solving this, obviously we're going to square root. Square root of 0 is just 0. So we're looking for when sine is 0 and cosine is 0. We should know how to do that, right? When does sine equal 0? Sine equals 0 at 0 and at pi and at 2 pi. And then looking at our interval that we're focusing on is only from 0 to 6. 2 pi is 6.2 something, so we can ignore that one. And then when does cosine equal 0? Cosine equals 0 when t equals pi over 2, 3 pi over 2. Those are going to be the only two that are in that domain there, okay? So now I know when the derivative is equal to 0. What I do from here is I set up a number line with these, what we call critical points. So when t equals 0 and t equals 6 are the two ends, and then we have pi somewhere in the middle there, and we have pi over 2, and we have 3 pi over 2. Okay? So these are our critical points, the t values when the derivative is equal to 0. Now we're going to input our w prime values. When t is 0, the derivative is 0. When t is pi over 2, the derivative is 0. T is pi. T is 3 pi over 2, the derivative is 0. Now when t is 6, the derivative is not 0, but that was the end of our interval. So I'm just going to put EP here for endpoint. Okay? That just tells me not to look any further than that. All right. Now, the next step is to figure out the signs of the function or the derivative function in each of these intervals. Okay? And the way we go about doing that is we pick any t value in between 0 to pi over 2 and plug it into our derivative function to see what kind of sign we get. If the derivative is positive at a point in between here, we know it will be positive throughout that entire interval. Because if it was positive at one point and negative at another point, what would that imply? That would imply that the derivative would have to be 0 somewhere between those two values, because you can't go from positive to negative without the value being 0 in between. And because we've already solved all the zeros, we know that that is not possible. So if we end up with positive at one point, it's going to be positive throughout the entire interval. Okay? Same thing with being negative within all those other intervals. So what I'm going to do is I'm going to look at my unit circle, right? And thinking about my unit circle, because our derivative function is all in terms of sine and cosine, what are the signs of sine and cosine within each quadrant? So we'll say for sine, I'll use the green, and for cosine, I will use red. For sine, the sign of sine is positive in quadrant 1. It's positive in quadrant 2. It's negative in quadrant 3 and negative in quadrant 4. And then for cosine, it's positive and then negative and then negative and then positive. Okay? Watch how this is going to help us out. Okay? We're going to go ahead and plug in a value between 0 and pi over 2. Let's say we plug in pi over 4. So if I want w prime of pi over 4, well, that's going to be equal to sine of pi over 4, and then all of that squared, times cosine of pi over 4. Now, I don't really care about the numeric value. I only care about the sign. So what is the sine of pi over 4? Well, the sine of anything between 0 and pi over 2 is positive. And then we're going to square that. And then what's the cosine of pi over 4? Well, that's positive also. So positive number squared is a positive, times a positive is a positive. So for every point in that interval, 0 to pi over 2, the derivative is positive. Then we go ahead and try a point in between pi over 2 and pi. So that might be 3 pi over 4. So now we're talking about quadrant 2 in this particular case. So that would be sine is going to be positive. So again, positive squared. But this time cosine is negative. So we're going to multiply that by a negative number. Positive squared is positive times a negative is a negative. And there's the bell. All right, you'll notice that I'm using this for my sine value. Sometimes I don't give you a trig function. You're just going to have to figure out the numeric values to figure out the signs, and that's okay too. But since this is all trig, I can use a unit circle to help me identify that. So for a point in between pi and 3 pi over 2, maybe 5 pi over 4, that would be in quadrant 3. So the sine is negative, but we have to square it, times the cosine is negative. So we have negative squared, negative times a negative is a positive, then times another negative is a negative. And then our last point we're going to concern ourselves with is somewhere between these 2 points, so I'll pick 7 pi over 4. The sine value is going to be negative, so we got negative squared. And then times the cosine value is positive. So negative squared is a positive, times a positive is a positive. Okay? So we have just determined the sine values of the derivative function for all the intervals from 0 to 6. Notice one thing. I told you guys to be careful about this in prior lessons. Don't just assume that it alternates always. And we can see here that it doesn't. We got positive and then negative, and then some of you go, well, then the next one's positive. Not here. Positive, negative, negative, positive. You can't just assume that the pattern will hold no matter what. So now that I know those values, I can say as a result of this, we can say W is increasing for 0 less than t less than pi over 2 and 3 pi over 2 less than t less than 6, since we want justification here, since w prime of t is greater than 0 over these intervals. Okay. All right. So since w is increasing, the amount of water is increasing, or the bucket is being filled. The bucket is being filled over this interval. One thing I'm going to put is inequality signs here. Why is that? Because when we talk about increasing, a function is increasing from point to point if the second point is greater than the first point. So we don't actually say that a function is increasing at a specific point. We say that it's increasing over an interval of time. Okay, so that's why we include the equal sign there, because we are comparing the endpoint, essentially, of that interval to the other endpoint of that interval. Okay? Now, some of you might say, well, w prime is not equal to, or is not positive at pi over 2. You're right, but again, we're talking about the interval. We're not talking about a point in time, and it doesn't necessarily have to be positive. It just has to be positive or equal to. Then we can also say w is decreasing, or in other words, the bucket is being emptied for the interval pi over 2, less than or equal to t, less than or equal to 3 pi over 2. Okay? And then same justification, since w prime of t is less than 0 or less than or equal to 0 or negative over this interval. Okay? So I want to express this. This is kind of important to understand. If you were to graph the function w, we can actually see the graph of the function w pretty well here. Because if w prime is positive, that implies that w of t is increasing. Then if w prime is negative, decreasing, decreasing, and then increasing. So what's this graph look like? It looks like it's going up, and then it flattens out to 0, horizontal tangent. Then it goes down, and then it flattens out to 0 again here. Okay? And then it goes down again, and then it flattens out to 0, and then it goes up again. Okay? So something along that line is what this graph looks like. Well, where is it decreasing? It's decreasing from pi over 2 all the way to 3 pi over 2. But the derivative is 0 at this point. Yes, but every point before it is higher than it, and every point after it is less than it. So that is a point that's included in that interval. That's why I only wrote one interval there. Okay. All right, so that's a great example of how to apply derivatives to a real life context. Okay, and we also got some examples with the chain rule here. We got some good practice with our unit circle and the zero product property, and basically all of mathematics wrapped into one question. So that's pretty cool. If you have any questions on this, I know the chain rule can be a little bit confusing at first, but if you have any questions, please comment below or reach out to me somehow, and I will do my best to help you out. Otherwise, don't forget to like and subscribe, and I will talk to you again later.